Okay, I'm back with my blue pen, and now we don't have any pictures, right? A 0.124 kilogram pine cone falls 45 meters from a tree. It is going 22 meters per second when it strikes the ground. What is the average force of air friction that acts on the pine cone as it falls? Right, and of course, it's like, well, it hits the ground. How is there a force acting on it? If you figure this out, what is it? It's v squared is u squared plus 2as, right? And the initial velocity is 0, so the final velocity should be the square root of 2 times 9.81 times 45 meters, right? And if you do that, the square root of 2 times 9.81. This is how fast it would fall if there were no air friction. Okay, times 45. You get that it should be going 29.7 meters per second. It's going somewhat slower than that, okay? 29.7. So the question is, where did that energy go? Well, I bet it went to force times distance, right? Okay, so let's solve the problem. Here it is. Here's the pine cone. Okay, okay, looks like a turd, sorry. Okay, and it's going to fall 45 meters. Okay, and let's see, when it's here, it's going 22 meters per second, right? And we want to know the force that acts on it as it falls, right? Okay, so I think what we've got is at the beginning we only have, when it's sitting here before it falls, I think it only has mgh, right? Right? And then I think that the energy, where does it go to? Well, the force of air friction will definitely be a slows you down force. Friction tends to be, right? So I think we got force times distance plus, it also has some kinetic energy, right? That's what I think is going on here. Okay, so mgh equals fs plus 1 half mv squared, right? That's what we've got. Okay, and the mass does not cancel out of all of these, right? Anytime you've got work in there, right? So 0.124 times 9.81 times 45 equals some force that we don't know, right? And then the distance over which it acts is 45 meters, right? Okay, and then 1 half, and then 0.124, and then what is it? It's going 22, right? And so to do this, what am I going to do? I guess I'm going to do this side, subtract that guy, and then divide by 45, right? Okay, so 0.124 times 9.81 times 45, 54.7398. Okay. Okay, whoops, I'm going to calculate this side. Okay, so 0.5 times 0.124 times 22 squared. That's 30.008, right? Get rid of that. 30.008. This is like, that's like a nothing there. Okay. And then I guess what I need to do is go this minus that, right? Okay, so 54.7398 minus 30.008. Got to get that 008 in there, right? I get 24.7318. Okay, equals F times 45. Divide both sides by 45. And I get F equals 0.54955 repeating. That is crazy. I love numbers. Okay, so let's see. That would be with 3 sig figs, I guess you'd have to say 550, right? Because if we're rounding to this place, you've got to go up, right? So that's why it says that. So force is about 0.550 newtons. Now, before we move on here, you just got to understand that the force of air friction on this thing is not going to be uniform. If you looked at it, if you made a graph of it, right, and you did distance here and force this way, right? It's probably, it's increasing, right? To begin with, when it's hardly moving through the air, it might not be much, and it might go up, and it might not even be linear, right? It might be like some curve like this. The cool thing is that what we figured out was the average force. So we figured out a rectangular area, but basically in general work is the area under a graph like this, okay? If you figure out whatever that area is under a force times distance graph, that'll be the work done. And what we did was we found an average force here.